Our problem set eight, the 8-1 problem, the whole goal was to analyze the CSTR reaction for A plus B equals R, or goes to R, using the kinetic expression. I started off by writing the CSTR mass balance, and then I substitute conversion so that all the flow rates were written in terms of F of A naught and X of A because the problem specifies a final conversion of 95%. I then use the F of A equals F of A naught and then 1 minus X of A and the CA equals CA naught and then plug those into the rate law along with the reactor volume. Solving this expression for FA naught gave the molar feed rate of A needed to hit the target conversion. Once I had F of A naught, I used the stoichiometry to calculate the production rate of R and converted it to pounds per hour using the molecular weight and yearly operating hours. For the energy balance, I applied the steady state CSTR heat removal equation, which includes what the sensible heat needed to bring the feed from 100 to 550 and the large exothermic heat return the reaction. By substituting in F of A naught Cp delta HR and X of A, I solve for the total heat that must be removed under the original conditions and scaled up. The final part examined how the Q changes when the production rate increases, showing that the heat load nearly doubles, meaning the existing cooling system would likely be very insufficient in what is going to be done next. For question 2 or 8-2 with along the Polynav solution, both were worked through the mass and energy balance for the gas phase reactor system using the variable flow rate, volumetric flow, and temperature dependent kinetic and thermodynamic data provided. I began by writing the rate law and used the ideal gas relationships at the inlet along with the given initial conversions to express the concentrations in terms of the molar flow rates and reactor temperature to set up the mole balance and a related CA to the conversion out of the expansion of V equals V naught and then T over T naught, P naught over P. After that, I set up the energy balance, which included the heat of the reaction term, the temperature dependent heat capacities, and the possible contribution from the heat transfer term. Rearranging this gave an explicit expression for the dT over dV that couples with the mole balance of the temperature and conversion evolved together throughout the reactor's volume. Finally, I solved simultaneously identifying how the temperature shifts the equilibrium constant and rate constant and determining whether the reaction accelerates or slows as it proceeds.